Okay, this is Geometry, Chapter 1, Section 2, Points, Lines, and Planes. This section is very definition heavy, not much in terms of calculations or computations, but basic definitions of geometric terms. So, um, I'll talk about it. I might write something that I might add on to the definition, but for the most part, uh, the book's definition seems to be adequate. So, the first thing they talk about is the concept of a point. And the book says the point indicates a location and has no size. So, in terms of a point, uh, the only thing you need to know in terms of a point is that it's a location device, right? Location. How does it? How can we differentiate one thing in space from another? Uh, we have this guy and we have this guy. Well, how can I tell these two guys apart in space? Well, I can have to tell these two guys apart is by just giving it some type of label and giving it some type of location, right? It could be a location in terms of some type of ordered pair or some type of other mechanism. And these points just help us tell one part in space from another. And it's usually represented by some dot and labeled. That is a point. A line, as the book says, is represented by a straight path extends in two opposite directions and uh, without end and has no thickness. The line contains infinitely many points. So a line is comprised of at least two points. In order to actually draw a line, you need at least 2 points. Um, so let's call this A. Let's call this B. It has two arrows, and the two arrows tells me that the line goes off in both directions, and notice that they're going in opposite directions. It goes on forever. So if I have the two arrows at the end, it goes on forever. Um, there's a few ways to label this line. The first way to label the line is if you notice there's a little lowercase l by the arrow, we can call it line L. We can also call it line AB. We can also call it line BA. What most people will probably do is call it line AB like this. You write uppercase A and B, you put the symbol of the line on top. You have to put the arrows, otherwise it's going to denote something else. So you do have to put the arrows on top. You can also put BA with the line symbol on top with the arrows. So those are the primary ways to label uh, a line. Then we have a plane. And the book says that a plane is represented by a flat surface that extends without end, has no thickness. Plane contains infinitely many lines. Let's go back to a line for a second, the last part. Uh, so I have a line. Within this line, the line is contained of points. Infinitely many points that goes off in either direction. So that's the last thing about a line. Okay. Plane. flat surface. And it goes off in two directions. It goes off in two opposite directions, either left or right, or up or down. And it is comprised of many, many lines, infinitely many lines, and those lines are comprised of many, many, many points. There are a lot of ways to label a plane. Notice that the ABC has dots, but there's a P in the upper right hand corner. The P could also be in the left hand corner, bottom right hand corner. And we could call this guy plane P, or we can call this guy plane ABC, or BAC, or CAB. The rule is that they have to be points, 3 points that has to be comprised of, and those 3 points cannot be on the same line. I repeat, those 3 points cannot be on the same line. So if I had a situation where I had some line on the plane, and let's say I called it horrible points. Let's say I called it XYZ. Sorry, I can't write this. Use down the space. What I can't call it is plane XYZ. And the reason why I can't call it plane XYZ is because plane XYZ is a straight line, and a straight line only goes in one direction, while a plane goes in two directions. Since it goes in two directions, we can't have something go in one direction and two directions at the same time. So you need to have 3 points that are not going in the same line. It has to be 3 points that are not in the same line. By the way, there's way more other ways I can call this plane, but with the 3 letters, but I'm not going to show every single one. But you get the idea. Linear and collinear. So if I had a line, I had points A, B, C. And if I had another line and called it X, Y, and Z, A, B, and C would be collinear. Because they reside on the same line. Points A, B, and C are all on the same line, so they are collinear. While X, Y, Z would be non-collinear. And they would be non-collinear because X, Y, and Z are not all 3 on the same line. So collinear and non-collinear. We also have planar and non-coplanar. So I'm going to draw a plane. And on this plane, I'm going to draw a line. And it's intersecting at point Q. we have a point T up here, and we have a point N, and then there's another line, and that's a Q, alright, P. That's fine. That's L, and that is M. Okay, so in this case, points R, Q, and S are coplanar. Why? Because all of those points are all in plane P. Plane P. While points T and N are non-coplanar. And the reason why they are non-coplanar is because they don't reside in the plane. So there's plane P, and T is way up here. T is going through the plane, but in a different direction than the plane. So T is outside of the plane, and N is outside of the plane. Therefore, T and N are non-coplanar. So we have collinear and non-collinear. We have planar and non-coplanar. So looking at this plane, they asked for two other ways to label line RS. So we can call this guy line SR. Remember with the line symbol on top. Q is within that line. Oh, we have that lowercase l right there at the arrow, so we could also call it line L. We could also call it, if we wanted to, line RQ. We can call it line QS. There's so many ways to label this line. As long as there's 2 points that resides on the line and they're collinear, that's perfectly fine. 2 more ways to name plane P. So remember we said plane P. This is what got it 1B. And this one was 1A. So remember we need 3 non-collinear points. So we can call it plane RVS. We can call it plane QVS. And there's so many other more ways to do it, but they only ask for 2. And then 1C asks you to name 3 non-collinear points. 3 non-collinear points. So 3 non-collinear points could be N, V, S. 3 non-collinear points. And then 1D says, what are 2 points that are not coplanar with RVS? So 3 non-coplanar points with RVS would be N and T, like we said earlier. Okay. Says the term point, line, and plane are not defined because these definitions would require terms that also need defining. However, use undefined terms to define geometric terms. Geometric sets points of space. So space is just all a set of points in 3 dimensions. So you don't have to worry too much about space, but we'll talk about those things that we can talk about within the space. So in terms of a segment, so this is a line segment, and we have some line segment AB. The first difference you should know between this and a line is that there are no arrows, just these points at the end of the line, since there are the beginning, depending on your point of view. And these guys are called endpoints. So B is an endpoint and A has an endpoint. The endpoint denotes the end of the line. So a line segment has a beginning and an end, or an end and a beginning. It does not go on forever. So when we label this, we would label this line segment AB. We put the line symbol on top with no arrows. Or we can call it line BA. Again, with the segment line on top, no arrows. That is a line segment. Then we have array. An array is comprised of one endpoint and one arrow. So one endpoint one arrow. Here, for a line segment, there's two endpoints. Two endpoints, no arrows. When we talk about line and when we talk about line segments, we were able to switch the letters, that B and A and B. You can't do that with arrays. Arrays are location specific. So the first letter will always be the endpoint. The first letter is always the endpoint. Every single time. So when I label this, I can only really label it with one letter. So since the endpoint starts with the letter A, I would label this AB, and I would put an arrow. So no arrow here, an arrow there, and that's how I label this ray. I cannot call it ray BA. Ray BA means something totally different, and it would mean this. In this case, the endpoint is at B, so we will write B first and then A with the ray symbol on top. This is ray BA. So it is location specific. If the endpoint's on A, then we start with A and call it AB. If the endpoint's on B and goes in the A direction, then we call it BA. Okay? Then we have opposite rays. Opposite rays shares the same endpoint. Opposite rays share the same endpoint. So if I have a line, call it A, C, B. The reason why they call it opposite is because they go in opposite directions, so they share the same ray or same endpoint. and they go in different directions. They share the same ray and they go in opposite directions. So in this case, we would say that ray CA and ray CB are opposite rays. CB goes in this direction, CA goes in that direction. They're going in opposite direction. One's going right, one going left, and they both share C. So C would be the first letter because that's the common endpoint that they share. And we would call that opposite rays. Alright, so naming rays. So we have this situation here. This is actually a really good question. So we have line DEF. And they ask you a pretty good question. They said, okay, what about ray EF? And ray FE. And they ask you, okay, they go in opposite directions, right? EF goes this way, FE goes this way. So since they both go in opposite directions, and they're both rays, then they should be opposite rays, right? But no, they're not opposite rays. And the reason why they're not opposite rays is because they don't share a same endpoint. They don't share the same endpoint. And that's one of the conditions. So you can have rays going in opposite directions. However, if they don't share the same endpoint, we can't call them opposite rays. Postulate or axiom. Nobody uses the word axiom too much, so we'll just call it a postulate. And what a postulate is a postulate is in geometry, is a rule that we don't have to prove. It is a rule that we don't have to prove, essentially. Some rule that you do not have to prove. That is basically what a postulate is. And since geometry basically deals with proofs and it deals with shapes, this is important. You don't have to prove. We're going to focus on things that you do have to prove a lot. So that is a postulate. So they're going to give us a whole bunch of postulates and rules that we don't have to prove. It's just common knowledge. And one of the common knowledges is that says through any line or through any 2 points, there's exactly one line. So let's say we have point A and point B. Let's say we have point B and point C. Well, this line that goes through A and B, we have 2 points, and these 2 points have only one line, exactly one line. Through any 2 points, there's exactly one line. And then we have point B and point C, and again, this line, exactly one line, goes through these 2 points. That is postulate 1-1. Through any 2 points, there's exactly one line. through any 2 points, there's exactly one line. Intersection is a point or a set of points that two figures have in common. So if I have a line and I draw another line, their intersection would be right there. Again, the definition is right there on the side, so I'm assuming you're writing the definition over there. Intersection is the point where the two geometric figures, in this case the two lines, share the same space at the same time. And that is an intersection. It can be one point, or it can be multiple points that these two geometric figures could share in space. And then that leads us to postulate 1-2. And postulate 1-2 says that through any 2 points, when two lines intersect. So here's a line, here's a line, here's a line, here's a line. We have 2 lines. When 2 lines intersect, they intersect to form exactly 1 point. So 2 lines, call it point P. 2 lines intersect. They form 1 point. When 2 lines intersect, they form 1 point. Postulate 1-3, I'll just say POS. And what postulate 1-3 says is that if we have 2 planes, and I can't draw 2 planes, I've tried, I can barely draw a straight line. When we have 2 planes that intersect, they form exactly 1 line. 2 planes intersect, they form 1 line. Let's say this word form. 2 planes intersect and they form 1 line. So postulate 1-2, 2 lines intersect to form a point. Postulate 1-3, 2 planes intersect to form a line. Another thing that you should know also, actually, and I don't know why they don't say this, but we could also have an intersection between a line and a plane. So if a plane intersects a line, so 1 line and 1 plane, intersect, they form 1 point. When a plane and a line intersects, they form 1 point. Alright, things that people don't like. They're going to show you a geometrical figure. In this case, they're showing you a cube. And the cube has tons and tons of endpoints. Again, I'm not going to draw the cube. So in this case, this cube has endpoint A, D, B, C, H, E, F, G, yada, 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 at the points of the cube. And what they want you to find out is various planes and lines that resides in this particular cube. And it says each surface on the box, they want you to find the intersection between ADC and BFG. So plane ADC would be this plane here on top. the top of the box, the top of the cube. Plane BFG would be the right side of the cube. So this guy is going in this direction, this guy is going in this direction, and when they intersect, they form a line. Remember, two planes form a line. And the line that they form, in this case, is going to be line BC, or you could write it as line CB. So two planes intersect to form a line. The top plane of the cube and the right side plane of the cube would intersect to form a line, and that line is BC. They ask you what are two names, what are names of the two planes that form BF. So I look over here, and this is BF right here going up and down. BF is going up and down. And it's comprised of two planes. And the two planes that it's comprised of is plane, you could say BCG, right? Three non-collinear points. And plane ABF. So the front plane, ABF, this square right here, and the right one, when they come together to form plane BF, and it would be going vertical. And I hate drawing cubes, but if I was to try to draw a cube, it would kind of look like this. Alright, it's not the best kid in the world. So this is A, E, F, this would be B, C, and G. So the two planes that are intersecting, they're going to form this line BF. So this is my line, right? So BF. So the two planes that's going to form line BF is going to be plane BCG, which is this guy, and plane ABF, which is this guy. So these guys come together, right? And when these two guys come together, the front of the cube and the right side of the cube, they come together to form this line BF, which is a vertical line going up and down. Two planes form a line. Why do you need only find two common points to name the intersection of two distinct planes? The reason why you only need to find two common points is because a line, only exactly 2 points fit within a line. So all you need is 2 points. So that's a postulate rule. Okay, postulate rule. Alright. So many definitions. Alright, postulate 1.4. It says that through any, there are any three non-collinear points in exactly one plane. Alright, postulate 1.4 says this. If I have a plane then a plane is comprised of three non-collinear points, or 3 points that are not on the same line. And we talked about this earlier. If they were on the same line, then that would make it a line. Well, a line only goes in one direction, while a plane goes in two directions. So we can't have something that goes in one direction represent something that goes in two directions. So in order to bypass that, you would need 3 points that are non-collinear. So 3 non-collinear points form a plane. That is postulate 1.4. and they give us examples to try to find different planes within a particular figure. Notice that this thing that's shaded here is JMP. Notice that it's a diagonal within the rectangular prism. So not only are the sides of the prism forming planes, you can also have planes that form diagonals within the prism itself. So 4a says what plane contains points L, M, and N? L, M, and N. So this would be a diagonal plane in here. If I was to, it's kind of hard for me to draw. So if I was to, and I'm really not good at drawing rectangular prisms, but I guess I can try. Okay, so I have this rectangular prism. I have J, N, M, R, L, K, Q, and P. And they ask what plane contains L, M, and N. So here's L, here's M, here's N, right? So they kind of form sort of a diagonal. So it would be this guy right here. Right, so this would be a diagonal cutting across here. And it would be plane, these three, so M, L, P, and N. That would be the plane. If I was to draw it, that contains that particular figure. Okay. Alright, and that's this section. I hope you guys have a great rest of your day.